All right, so we're lucky today to have Dr. StevenEhlert, who is a NASA scientist who supports a number of X-ray astronomy missions at Marshall Space Flight Center in Huntsville, Alabama. Dr. Ehlert received his BA in Physics and Mathematics at Northwestern University, graduating in 2007. After a one-year fellowship at the Max Planck Institute of Nuclear Physics in Heidelberg, Germany, he got his PhD in physics at Stanford University, graduating in 2013. His thesis was advised by Professor Steve Allen and was entitled The Coevolution of Galaxies and Their Surrounding Environments in Massive Galaxy Clusters. After graduating from Stanford, he worked as a postdoc at MIT and soon after joined the Marshall Space Flight Center to work as a contractor in the Meteoroid Environment Office in 2014. He then returned to his X-ray astronomy roots in November of 2019 and is now a civil servant scientist in the astrophysics branch at Marshall Space Flight Center. And Dr. Ehlert's primary research field of expertise is in the astrophysical processes that operate within the most massive structures in the universe, galaxy clusters, in particular regarding the populations of galaxies residing within them. He has co-authored more than 20 peer-reviewed journal articles on a wide range of topics, varying from galaxy clusters and active galaxies to comets and meteoroid impacts on the moon. He loves to talk about science and research with the next generation of young scientists, and in his talk, he will do exactly that by discussing the wide variety of critical tests of fundamental physics and astrophysics that can be performed with galaxy clusters. So please take it away, Dr. Ehlert, and we're looking forward to your talk.
Okay, so thank you everyone for listening. It's a pleasure to be here. As was alluded to in the introduction, there are lots. I'm an X-ray astronomer, and I work with many missions, and they're all in different stages of development. But while they all have different specialties and very specific targets and missions they're looking to do, they all observe some of the most spectacular, extreme, and sometimes violent objects in the universe. So that's what X-rays are really good at observing, and today is going to be a talk about one of those objects, one of those classes of objects, called galaxy clusters. So I did my PhD thesis on X-ray observations of galaxy clusters, primarily using data from an X-ray telescope called Chandra. It's named after the astrophysicist Subrahmanyan Chandrasekhar, who made a tremendous number of contributions to our understanding of stars, galaxies, and gas in the universe. His most famous work was developing a model for the structure of white dwarf stars that predicted a fundamental limit to their mass, 1.4 times the solar mass, which is known as the Chandrasekhar limit. So many galaxy clusters are part of the Science Olympiad materials for this year, and I'll try and describe some of these objects in detail later on. In particular, what I really want to emphasize in this talk, and what I'm going to try to do, is just point out how big these objects are. So one unfortunate side effect of working with big astronomical objects all day, like I do, is that you sort of become numb to the sheer scale of what it is you're observing. So hopefully by the end of this talk, you'll appreciate just exactly how large these galaxy clusters are. And at the same time, I've looked over some of the materials and some of the key objects you guys need to know. So I'll try and weave those in as it makes sense. So if something doesn't make sense, if there's concepts that don't really make sense, make sure to study up on them. They're probably in your materials. So I'll start with sort of the big question of what are galaxy clusters and why would anybody want to observe them in the X-rays? So the very simple descriptor of galaxy clusters, and there's an image of one that you can see up on the screen, is that they are the largest gravitationally bound structures in the universe. As the name suggests, they host many, typically of order hundreds or even thousands of galaxies, all orbiting around a common center. They're all in a single gravitationally bound system. It's not all that different from all of the planets orbiting around the sun, although the orbits can be significantly more complicated. So this is an image of a galaxy cluster from Hubble, taken at optical wavelengths. And the majority of this talk, I'm going to be discussing all of the constituent components of these clusters, what they're made out of, because the galaxies are only a very small part of the picture, only a tiny fraction of the total mass. And at the end of this talk, we're going to have a few discussions about how these different components interact with one another and what they can teach us about the universe at large. So how big are these? How big is, I mean, this is an image, and the image takes up a sizable amount of my slide screen, but how big actually are they? And I made this nice little table to help really point out exactly how large a galaxy cluster is. So in this first column, you see a bunch of objects, some of which will be familiar from your material, some may not. and then just how massive they are in units of the sun, which is generally the unit you use for astronomical objects of any size. Certainly anything bigger than the sun is almost always in units of solar masses. So we start with the Earth, which is 3 millionths of a solar mass. And you see here that I actually have everything written out very explicitly, just because while scientific notation is nice and compact, it also sometimes makes it very easy to forget exactly how much bigger certain numbers are than big numbers are than small numbers. So the Earth is about 3 millionths of a solar mass. The sun, by definition, is 1 solar mass. If you look at a globular cluster, such as M13, we're looking at about 600,000 solar masses. A supermassive black hole, like Sagittarius A star, at the center of our galaxy is about 4 million solar masses. An even larger supermassive black hole, like the one at the center of the galaxy M87, would be about 6.5 billion solar masses. The Milky Way galaxy in total is about 1 trillion. And then we get to the galaxy clusters, which are at least approximately 100 to 1,000 times more massive than that. So the Virgo cluster is about 10 to the 14 solar masses, and a really massive galaxy cluster, such as Max J 1149.5 plus 2223, and we'll discuss what that means later, gets up into about 2 million billion or 2 quadrillion solar masses. So the next question, now that we know how big they are, the first question I started to ask is, how do these objects form? How do you build something that's so big? And the answer, and we'll see this in a video in a little bit, is from the bottom up, sort of one star at a time. Also, is sort of fundamentally kind of how it gets built up. Stars and star clusters form first in the early universe, and then merge with each other to form galaxies. And then groups of galaxies are sort of drawn to sort of the highest concentrations of mass to form even larger and larger structures. And you can see all of this in a video. So this video is from a simulation known as Illustris TNG. And the colors here, I was just going to give you a heads up as to what's going to happen in this. The colors here denote the speed of the gas. So you see sort of a picture of some visualization of the gas, and we're going to see it moving around and accreting and coalescing into larger structures as time goes on. Up here in the top right corner, what we're going to see is, up here in the top right corner, we're going to see the redshift. And the redshift is basically the clock. As the redshift goes down, we're looking at later and later times. And I can't discuss redshift too much in this talk, but basically, to give you an idea as to how things scale, a redshift of 3 is about 11 billion years ago. A redshift of 1 is about 6 billion years ago, and today is a redshift of 0. And the universe is about 13.7 billion years old in the simulation. So it's not a straight line. It's not like redshift 6 is twice as old as redshift 3, but basically as the redshift goes down, time's moving forward. So let me play this now. Oh, the other thing to note is that about halfway through, we're going to transition from seeing the gas visualized to a grayscale video of the starlight. And there it'll be very clear where the galaxies are. So let's see this gas, which starts out more or less uniform. More or less uniformly distributed. But we can see these filaments start to form. And these filaments, in particular where they intersect, are really going to be where these clusters start to merge. And you can see one cluster, sort of gas flowing onto one cluster here. And you can see some accretion over here, where everything is really starting to merge and intersect. And you see the simulation has galaxies outbursting and ejecting, and there's mergers and sonic booms. And you can see all of that in the speed. So as these speeds change color, we can also see as time's moving forward, the colors are getting brighter and darker, which means that things are moving the gas is moving faster. This primarily has to do with the fact that our gravitational wells are getting larger. So everything can start moving more quickly, and you can see all these eruptions. And right about now, you can see we're right about redshift 1, so a little over 6 billion years ago, and you'll see it start to transition into galaxies really soon. And now what we're seeing in grayscale is all the starlight. So you can see the galaxies as these discrete little tadpoles, and you can see we have two clusters now, one here and one here. And as this video reaches the present day, we're going to see these two galaxy clusters, these two large galaxy clusters, merge into an even larger single system. And we have these two big, bright central galaxies. These are sort of the biggest galaxies in the clusters, are right at the center, and they merge into an even larger galaxy at the end. And there's our big cluster. All right, and there are the credits, so I'll leave it there. Okay, and there we have it now. So we saw the gas moving around, and we saw the galaxies moving around. And as I mentioned, the galaxy clusters are far more than simply galaxies. And in fact, only about 1% of the total mass of a galaxy cluster originates in the galaxies themselves. So there's a factor of 8 to 10 more mass in a diffuse intracluster gas that surrounds all of the galaxies. But even that is dwarfed by dark matter, this mysterious but ubiquitous form of matter that we don't know all that much about. I'll talk a little bit more about this later, but basically all the evidence suggests it's a form of matter that's very, very different than what we are observing, than what we interact with every day. And all of these components can interact with each other as well. And because of those interactions, we can gain all sorts of useful insights into galaxy evolution, the formation as to how structure forms in the universe, and even some constraints on the large-scale properties of the universe itself. So I'm going to focus on these three components and give you a brief overview of what we know about them. And then at the end, we'll talk about how those actually lead to new results in terms of astronomy. So the first one I'm going to talk about is known as the intracluster medium, this diffuse gas. So what do we know about the intracluster medium? What do we know about the ICM? That's the abbreviation for it. So the ICM is a commonly observed gas in X-ray observations of galaxy clusters. So this is a real Chandra image. This is an image using real Chandra data that I took from a paper I wrote about 10 years ago of a galaxy cluster known as MaxJ 1931.8 minus 2634. And what this shows you the positions of X-ray photons that were detected by Chandra and their sky coordinates. So you can see that there's a coordinate grid here, and you can see kind of where the name comes from, because you can see where the center of the X-ray emission is, kind of right where I'm pointed. So right here where my pointer is, this is sort of the center of all of the X-ray emission. It's the center of the cluster. And you can see based off of this grid that it's located at right ascension, 19 hours, 31 minutes, and about 50 seconds, based off of this. And then the declination is about minus 26 degrees, 34 minutes, and 30 seconds. So I should also point out the scale of this image. So at the distance to the cluster, this black bar up here is 200 kiloparsecs. So remember that 1 parsec is about 3.26 light years, which means that this black bar corresponds to about 650,000 light years. So what we're seeing here is we're seeing X-ray gas, X-ray bright gas that spans about 1 million light years across from top to bottom. So what else do we know about it? Now, using the same Chandra data, we can actually measure the thermodynamic properties of this gas. And by thermodynamic properties, what I really mean are sort of temperature, density, and pressure. So an X-ray telescope lets us do this because it doesn't just measure the positions of X-rays that arrive, but it also gives you some insight as to the energy of those photons that hit the detector. So by counting the number of photons that you observe at each individual energy and comparing it to the full ensemble of energies that the telescope is sensitive to, you can create a spectrum, what's known as a spectrum, and actually estimate the temperature of the gas. And you can measure the density as well, because basically what we know, or basically for a thermal gas like this X-ray gas, what we expect is that the total number of X-rays that you'll observe is scales with density squared times temperature to the 1/2. So that total number, combined with the fact that we know how many photons there are at given energies, let us measure the temperature and the density of this gas. And here you can see a temperature profile. So basically what was done is little annular regions were laid down, and all of the photons in each of those little annular regions, starting at the center, were collected, and the temperature and the density were measured from its spectrum. And when you do that, you get these measurements. Both of these colors correspond to the same measurement and the same data with just some slightly different methods. And the size of the region is denoted by the horizontal error bar, while sort of the uncertainty on these temperature and density measurements is quantified by the vertical error bar. So a couple of things I want to point out about the scales of galaxy clusters. So the temperature in this plot, which was taken straight out of a paper, is in units of what are sort of units that are very convenient for X-ray astronomers, known as keV. And you don't need to know exactly what a keV is, but what you do need to know in terms of comparing it to things you encounter every day is that 1 keV corresponds to about 11 million degrees Kelvin, or 11 million degrees Celsius or Fahrenheit. The scaling doesn't really make a big difference at these temperatures. So what we're talking about is temperatures in this galaxy cluster range from about 30 to 100 million degrees, which is hotter than the core of the sun, not the surface of the sun, the center of the sun. And looking at this density plot, this is the electron density for reasons I won't get into here. But this electron density that we're measuring is about a tenth of an electron per cubic centimeter, or 1 electron in a 10 cubic centimeter box. For comparison, because that's not particularly insightful in and of itself, I want to compare it to just a balloon that you would inflate, which would have a standard temperature and pressure about 3 to 10 to the 20 electrons per cubic centimeter. So we're talking a factor of 1 billion trillion discrepancy between the densest part of a galaxy cluster right here and a balloon that you just inflate to play with your kids, or at least I play with my kids. So my kids love balloons. So anyway, with these two numbers, we can also calculate pressure. Now, to remind everybody of some high school chemistry, or preview some high school chemistry for those of you who might be really young, we have an ideal gas law that says PV equals nRT, which we can rearrange to say that pressure is equal to basically number divided by volume times a constant times temperature, which are exactly these two variables. So this is the number in a given volume, and this is the temperature. So it's exactly the two variables we have here. So we can measure pressures. The other thing I want to say is why this gas is so bright in the X-rays is that for any thermal emission, anything that's sort of emitting because of its temperature, the typical energy of the photon that you expect to receive is approximately a constant times the temperature of the object. And K, that's known as KT. And K is a number known as the Boltzmann constant that has a value of 1.38 times 10 to the minus 23 joules per Kelvin. And when you actually run that through with these temperatures of about 30 to 50 to 100 million degrees, the typical characteristic energy of those photons is in the X-rays. So that's why the X-rays are really good for observing the hot gas. Now, Chandra could do even more than simply give us these profiles. In fact, because it has such good spatial resolution and it collects so many photons, we can actually measure the temperature structure of the galaxy cluster in 2 dimensions. So this is sort of a projected map of the temperature of the same galaxy cluster. The field of view is almost identical to what we observe in this image right here. You'll see the 200 kiloparsecs is a little bit bigger. So it's a little bit zoomed in, but you can see we have this cool region right here. And we also have this cool spiral of gas that's sort of flowing in towards the center. Now, you're probably wondering, why is the center cool? If you think of the sun, the center of the sun is way hotter than the surface of the sun. If you think of the Earth, the center of the Earth is way hotter than the surface of the Earth. Well, the reason for this actually has to go back to how that energy is emitted. So the total energy of a galaxy cluster, the total thermal energy, is basically density times temperature, whereas the total emission that's the total energy per unit volume, whereas the total emission per unit volume, as I said, scales as density squared times temperature to the 1/2. So you can actually calculate the time scale where you'd expect the gas to cool just from emitting photons, just the energy loss from emitting photons. And that actually scales as 1 over density, because n over n squared, times temperature to the 1/2, because of temperature over temperature to the 1/2. So it's actually those denser regions that'll cool the most quickly. So that's what we're seeing here. And features like this spiral of cool gas and other structures that you can observe in other galaxy clusters in their temperature or their pressure structure give us a great deal of information as to how these massive structures formed and what their histories were and how they're going to be evolving in the future. So with that discussion of the intracluster medium, now I'm going to move on to the galaxies themselves and what we know about those. The first question, one big question that people are continuing to investigate is, are galaxies and clusters unique compared to isolated or field galaxies? The short answer is yes. And to sort of describe why, I'm going to look at this sort of classic Hubble tuning, what's known as the Hubble tuning fork. So this is how Hubble classified galaxies as he observed them in the early 20th century. This classification scheme, in terms of our modern understanding, is a bit outdated. There's still many aspects of it that are still in use today, but it does give us some very useful visual cues for looking at these galaxy clusters as we move forward. So over here, we have the elliptical galaxies, and the number corresponds to how elongated they are. So the E0s are very round, the E6s are very elongated. And then it forks off into the spirals and the barred spirals. So here we have our spiral galaxies, and you notice as we sort of move our way in more and more spiraled, we see that the color changes from sort of this yellow color, which in astronomical we call redder, and to these bluer colors, which in astronomical sense we call bluer. And then we have, and it's the same for these barred spirals. Sort of the more spirals we see in these SBs and SCs, they tend to have bluer colors. Now, looking back at our original image of a galaxy cluster, you see there's a lot of yellow elliptical galaxies here. That's what we're observing. Most of these galaxies are yellow and elliptical. There are not many blue spiral galaxies. But really, the cluster is seen in these redder colors, as an astronomer would say. And the color of a galaxy has a very straightforward physical origin. At optical wavelengths, what we're observing is primarily the sum total of all of its starlight. So if a galaxy is blue, what we're observing is lots of young blue stars. And if a galaxy is red, or sort of visually yellow in a lot of these press images, then only what we're observing are sort of only the older red stars. So the color actually maps very, very well with the star formation rate of the galaxy. So red galaxies have low star formation rates, and blue galaxies have high star formation rates, because when they have low star formation rates, it means that there aren't a lot of young blue stars being produced, because those young blue stars only live a much shorter amount of time than the low mass red stars. So what we find in galaxy clusters is that the majority of the galaxies are red and dead. They're elliptical galaxies with mostly red and dead elliptical galaxies with only a few bluer spiral galaxies. Now, this can be seen more clearly if we plot up the colors and magnitudes of all the galaxies in these images. So this is what's known as a color magnitude diagram. This is for two galaxy clusters at different redshifts, so at different distances away from us. And what we're seeing is on the x-axis of this plot, we're seeing the magnitude, basically how bright the galaxy is in a particular filter, and I'll discuss this in a sec. And then on the y-axis, what we're seeing is the color, which is basically the ratio between the ratio of a galaxy's brightness in two different band passes, at two different wavelengths. And all of these sort of bold crosses here, the bolder points, these are members of the galaxy cluster. And this is known as the red sequence right here, because you can see it's a bit redder. Looking at the y-axis, redder goes up and fainter goes to the right. So you can see it's kind of on the bright end of all these little dots and redder than many of them. This is known as the red sequence. And this red sequence of galaxies is so ubiquitous and it's so well measured in galaxy clusters that if you just had an image with a bunch of sources in it, you could actually use this red sequence to figure out if any galaxy clusters are there. And that's how a lot of galaxy clusters are found, is you gather a catalog of many, many millions of objects, and you find clusters of objects in these same colors and in these regions of color magnitude space. You look for this red sequence. You'll notice that the location of this red sequence changes. You can see between this lower redshift cluster and this higher redshift cluster, we've moved fainter, i.e. to the right, and we've moved redder, i.e. up. So here the color is about 1, here the color is about 1.5. I also thought it would be useful to remind everybody who's studying up for the competition about their magnitudes. So the G, R, and I here, these are filters. So each of these corresponds to a specific band pass of, specific range of wavelengths that are used to observe these galaxies. So the I band observes light at the reddest wavelengths. The sort of I band is kind of the reddest wavelengths that the human eye can see. The R band is a little bit bluer than that. It corresponds to what our eyes see as yellow and orange. And then the G band is sort of our blues and our violets, and it even has a little bit of coverage into the UV. So it goes a little bit bluer into a little bit shorter wavelengths than what the human eye is sensitive to. Finally, I will remind you that magnitudes are a logarithmic scale with brighter sources having smaller magnitudes. And the scaling is set up such that 5 magnitudes difference corresponds to a factor of 100 in brightness. So these magnitude 15 sources right here are 100 times brighter than these magnitude 20 sources over here. Finally, don't forget that the human eye on a really clear night in a really clear sky in a really dark site can see down to about magnitude 6 on a really good, if they're lucky. So what that means is that all of these objects are about 10,000 to 1,000,000 times fainter than the human eye can see. So how does that red sequence form? There are lots of different processes for the galaxies and the clusters that operate in the clusters. And all these processes operate for field galaxies, but they tend to be more extreme in the cluster environment. So I'm going to discuss a few of these in detail. The first one is known as ram pressure stripping, and you can see it in this little cartoon here, where a galaxy is moving through the gas, moving through the intracluster gas, and ram pressure is basically the force you experience as you're moving through a fluid. So as your car drives and you feel that, as you're driving a car, if you're driving a car driving a convertible and you stick your hand up and you feel the breeze coming past your hand, that's ram pressure. And because of the extent of the pressure and the speeds of the galaxies moving through the ICM, the galaxies move through the ICM at about 1,000 kilometers per second. What can happen is that ram pressure can actually strip gas that's hosted locally by the galaxy from the galaxy itself, and it gets deposited into sort of the ambient ICM. And it can leave these big spectacular tails in its wake. So you see these wakes sort of trailing behind the galaxy, and that galaxy itself is losing lots of its own stash of gas. And that affects its star formation rate moving forward. Another thing that happens a lot in cluster galaxies are mergers and tidal interactions. So mergers are just what you think they are. It's when two galaxies collide together and form a larger galaxy. mergers actually don't happen as often as you would think, because even though there's a lot of galaxies around, they're moving so quickly with respect to one another that they generally don't merge. They generally don't get drawn into each other gravitationally to where they merge. What happens far more often is what's known as a tidal interaction, where two galaxies are moving past each other at high enough speeds where they don't merge, but because gravity is a sort of a 1/r² force, this side of this little galaxy right here has a stronger attraction to this side of this little galaxy right here than sort of these outer regions do. So what happens is these two regions get pulled towards one another more than these two regions get pulled towards one another. And you end up with an elongation like this. So as these two galaxies keep moving on, keep moving away from each other, they sort of have these longer tails extended in the direction of their interaction, in the direction of where they cross. And if you have many of these, and you can have many of these repeated interactions over time, this is known as harassment. Now, I will show you what a few spectacular images of merging galaxies look like. These are not mergers or tidal interactions specifically for galaxies and clusters, but the physics is more or less identical for these merging systems as well. So you can see that you can see these long tidal tails, you can see these interactions, you can see a few colliding, and they're all in different stages of merging, and they're all, some of these can be very violent collisions, as you can see. Now here's a visualization of ram pressure stripping with a galaxy known as ESO 137-001. It's undergoing ram pressure stripping. The stripped gas is actually shining bright in the X-rays. It's hot enough to be an X-ray emitting gas. It's this faint blue emission right here. And you can see it. And the spiral is being stripped as the galaxy is moving through a cluster in this direction. It's kind of moving up and to the left here. But the ram pressure stripping is so severe that we actually see the gas extending for 250,000 light years. So by looking at the gas in these systems, we're not only able to learn about the fate of the galaxies and how these galaxies are going to evolve, but we're also able to understand how this gas that's been stripped interacts with the other intracluster medium that we're observing, and how it's ultimately going to mix and enrich this gas, the intracluster gas. So this gas is so hot, so magnetic fields are important, and the behavior of plasmas are important. Understanding the plasma properties of the gas are very important. And that's going to play a crucial role as to how these two phases of gas will ultimately mix together. The stripped gas from the galaxy and the surrounding ambient cluster gas. But it turns out that the interactions can go the other way as well. So we've talked about how the gas influences the galaxy, but the galaxies can actually have a reasonable influence on the gas. So in particular, it's the central galaxies, such as M87. M87 is a very popular galaxy for reasons I'll get into very shortly, that is at the center of the Virgo cluster. So this central galaxy actually has a very important impact on the intracluster medium surrounding it, which would be observed here. So M87 is the central galaxy. The central galaxies are usually tremendously large. You can see just visually how big M87 is compared to some of these other galaxies next to it, which are all more or less at the same distance. So as I mentioned earlier, the central regions of galaxy clusters can be cooler than the outskirts, than sort of the regions a little bit further away. And if that gas has had enough time to cool, then it can actually start falling onto the central galaxy. And when too much gas falls onto the galaxy, it falls onto its central supermassive black hole. And the supermassive black hole would be right inside this box. And when too much cold gas ends up accreting on the central black hole, we get jets of material that are launched that uplift and heat all of that cooled gas right at the center. And this actually is one of the most efficient ways of extracting energy in the universe. So I just want to show you how influential these central black holes can be. And I want to start by showing you this image here of M87 taken last year by the Event Horizon Telescope. So So if there's enough gas falling onto the black hole, the galaxy becomes an active galaxy, as it's known. And here's M87, as imaged by the Event Horizon Telescope. This was a really awesome image. I loved seeing this image come through because it's just such a spectacular image. This is M87's black hole. This is what you're seeing in the center here. This dark region is actually the black hole. And right where it starts to brighten, that's the innermost edge. That's the event horizon of the black hole that we're imaging here. So M87 is about 53 million light years away. And this image was created by basically pointing every massive radio telescope on the planet directly at the galaxy in order to create a mega telescope that has an effective diameter comparable to the Earth, the size of the Earth itself. And the signals from all these radio telescopes need to be painstakingly correlated with each other extremely carefully, and then the image had to be reconstructed from those correlated signals. And I believe it took about a year for the final image to be produced after receiving all the data. Just sort of correlating all the data and analyzing it and building this image took about a year. And it was an incredibly involved process to make this image. It's not particularly relevant for the rest of the talk, but I thought it was just a really cool aside. And I believe M87 is one of the big topics on the Olympiad materials this year. So the key thing to point out is that the black hole, sort of the width of this image is about 2 light days. So it takes about 2 days for light to go from here to there. So let's guess as to let's wonder how big the sphere of influence of this black hole can be in terms of the gas. And the answer is about 100,000 light years, or 35 million light days. So we went from about 2 light days, a region of the size of about 2 light days, influences basically the temperature structure on a region about 35 million light days. So in terms of proportions, what that means, the equivalent would be if you had an army tank that could shoot to the moon, or a volcano like Mauna Kea or Mount Vesuvius ejecting dust to Mars. That's kind of the proportions we're talking about here. So this is M87 on a much larger scale. This is an X-ray temperature map, similar to the temperature map I showed a few slides ago, that shows the temperature of the gas around M87. M87 is a lot closer, and it also has a lot more coverage. So you can make these really beautiful maps because you just have a lot more data. You can measure smaller regions, and you can measure them really well. So this one, I always thought it just looked like a painting, but this is actually these are real measurements of a real galaxy, or of real gas around a galaxy. And these long yellow structures here, these are plumes of the cold gas that originated right here at the center that were uplifted by the central black hole. So this is very much kind of a volcano where this gas is starting out really close to the central black hole, and the volcano erupts, and this gas gets launched out for incredible distances to much higher altitudes than ever before. So now we know about the galaxies and the gas, so I'm going to talk a bit about the dark matter. So I am not the expert on dark matter. I don't know if there's anybody slated to talk about dark matter moving forward, but I'll try and give everybody a quick introduction to dark matter so that you at least have a basic understanding of what it all means. So it's probably best to describe dark matter or what it is not before I really describe what it is. So dark matter is fundamentally different, at least to the extent that I can understand its properties. It's fundamentally different from protons and neutrons and electrons that we interact with every day. In fact, even all of the more exotic particles that we observed in a particle accelerator, like the Large Hadron Collider at CERN, can't account for dark matter. Dark matter doesn't it doesn't have any charge. It has no interactions it has no electromagnetic interactions to speak of. And in fact, if you look at the standard model of particle physics, there's really no spot for dark matter. There's nowhere on the table that's missing. There's nowhere in the standard model to accommodate a dark matter particle. But the observational signature we have of dark matter is its gravity. There are astronomical objects on lots of different scales that require far more gravitational binding energy than what can be accounted for from the stars and the galaxies and the gas. And galaxy clusters are one of these systems. They're actually, in many ways, one of the most compelling systems for searching for dark matter. So let's ask how we know that there's dark matter in galaxy clusters. How do we know it's 90%? And how do we measure the mass of a galaxy cluster in the first place? And how do we know we're not overlooking something that's just ordinary matter as opposed to resorting to dark matter? So I'm going to talk about how to measure the mass of a galaxy cluster really quickly. I'm going to describe two methods. These are not the only two methods, but they are two, and I want to talk about how it's important to have more than one. So the first method is by assuming that a galaxy cluster is in what's known as hydrostatic equilibrium. And what that means is that the pressure that the pressure of the gas in the cluster is balanced out by the gravitational pressure. Pressure holding it up is balanced by the force of gravity pulling it in, or pulling it down. And this is an image of the sun that sort of describes the same thing. The sun is in hydrostatic equilibrium. You don't see it rapidly expanding or contracting, at least not on a level of, at an appreciable level. And by appreciable level, I mean even 1% of the size of the sun. So the sun is in hydrostatic equilibrium, and the physics is identical for a galaxy cluster. So we can, as I mentioned early on, we could measure the thermal pressure as temperature times number density. So very similar to what I had for the density profile, you could come up with a pressure profile. And from that thermal pressure profile, you can calculate how much mass would be required to keep the system in hydrostatic equilibrium. And from there, what you measure is something significantly more massive than the mass of the gas itself, or the mass of the galaxies for that matter. So there's lots of other questions one could ask is, how do we know that the gas in a cluster is in hydrostatic equilibrium? Or how do we know there aren't any other significant sources of pressure other than the thermal pressure? Of course, there could be, there's lots of pressures you could imagine. There's lots of pressures that we interact with every day, and there could be some equivalent on an astrophysical scale. So what's convenient is, as scientists, we can test those hypotheses, and the full testing procedure and all the tests that can be done is a bit beyond the scope. But there is another test, and it's another way to measure the mass. And that is with an effect known as gravitational lensing. So gravitational lensing is a consequence of Einstein's theory of general relativity. And what it leads to is measurable distortions in the positions and shapes of objects behind another massive object. So there's a source, and in between there's a lensing mass, which here is represented by the galaxy, before it reaches our telescope. So the way this works is that we have a real source. If you had a full map of the universe in front of you, it'd be located here. But this real source, this real quasar or active galaxy, is behind another massive source, another massive galaxy. So, and the fact that there's this mass here, it bends the light around. It bends the light that comes off of the real source, the real quasar. So instead of the light making its way straight to us as a straight line across, really it's these photons that started traveling this way get bent around to reach our telescope. And at the same time, there's another photon that goes a completely different direction that also reaches our telescope. Now, just by physics, the telescope can really only infer the positions from the straight line back from where it observed it. So what we see is we see quasar images here and here as opposed to the real source being located here. And there's lots of very different configurations of this, but if it's aligned just right, you can see multiple images. And just as interesting about these multiple images is that the time it takes does not have to be the same between these, depending on the precise alignment. The time it takes to take this path may not be identical to the time it takes to take this path because the distances are different. So what that means is you could see variability in one image of the quasar that you don't see in the other, but you may see this one earlier or later in A than you did in B. So what this means for measuring cluster masses is that the number of images you see and where they're located is going to depend on the enclosed mass, or basically the mass enclosed inside of those images. So you can measure galaxy clusters using these lensing effects. It's a very complicated measurement, but it certainly can be done. So gravitational lensing also creates these arcs creates these arced galaxies around the cluster. And these are like for example, these arced blue galaxies are usually behind the cluster, and they're being lensed to look like they're sort of off to the sides. Whereas in fact, their real position would be closer to sort of the center. And if you look very carefully, and you blow this image up and you look very carefully, you may also see that a lot of the shapes are a little bit distorted, and they're distorted in such a way that sort of on average, they sort of trace circles or ellipses around the cluster itself, around the center of the cluster. So that gives you another idea as to how much mass is here, how much mass is enclosed in each region. So when these two measurements are done for an ensemble of galaxy clusters, and it takes a lot of work to make these measurements, but once they're done, it turns out they both agree. They both agree pretty well. So that gives you an idea that gives you a stronger indication that the mass that you're observing in these clusters is significantly more than what you're observing in the gas itself, or the gas plus the galaxies. And you should also notice, I also want to point out that these are very different measurements. They're sensitive to different things. They're sensitive to different performance metrics. They occur primarily at different wavelengths, and there are different assumptions made in each one of them. So the fact that they agree gives you a much higher confidence that the measurement is in fact correct than either of these could give you individually. You're not just more precise, but you actually have a lot more faith in the accuracy because both basically certain parts of what sensitivities in one measurement are not an issue in the other. So this is a very common technique, is a very common thing that astronomers like to do. They like to measure certain properties of certain objects multiple ways, if at all possible, to really beat down those uncertainties in each individual measurement, which could be systematic. That there's the limitation to the experiment and limitation to your instruments or your observing methodology, just fundamental to one measurement that aren't an issue in a different measurement that's done independently. All right, and it's these combinations, the lensing, the galaxies, and the X-ray gas that really allow fundamental physics tests to be performed. So what I'm going to do for the last couple slides is point out three different galaxy clusters that are in the Science Olympiad materials and discuss what makes them so cool and what sort of tests can be done. So here are three. So the first is this cluster 1E0657-56, known as the bullet cluster. This is a collision between two nearly equal massive clusters. So you'll notice on this image, and the next two images will be the same, that it's basically going to be a background of Hubble, and I will label all the different colors, because the colors are going to change. These press images are designed to look awesome, and sometimes you need to reuse colors for different wavelengths, and sometimes they're not consistent from image to image because it's really not the most visually striking, because these colors are very visually striking and you don't always have the same data. So the yellow, sort of this background, is a Hubble image. The pink here is the X-ray gas. So this pink is the X-rays. So you see sort of two big features here of bright, hot gas right next to each other. And this bullet gives you an idea as to how this cluster is moving, and this one is sort of moving from the left to the right over time. And this arises from the interaction between sort of one cluster's gas and the other cluster's gas. And the blue here is the lensing-derived mass. So this is where all of the mass in these clusters is. And you'll notice it's separate from the pink, where the gas is. And you'll also notice that the blue is sort of concentrated where the galaxies are. You see all these galaxies here. They're sort of, the blue is sort of superimposed right on top of them. And the same thing over here. So this is an incredibly important system for us understanding dark matter, because in this collision, we can actually see that the mass, the majority of the cluster mass, has separated from the majority of the cluster gas. So this is demonstrating that whatever the mass of this, the majority of the mass operates more like a collisionless galaxy. The galaxies are just flying straight through each other because they're so small, as opposed to a collision full gas. The gas, you can imagine, is just sort of two phases of fluid colliding in with each other. So it's mixing and mashing and dragging. So it's the drag between the two gases has slowed it down and allowed the dark matter to escape. This is actually, to this day, this image came out in 2006, but to this day, this is probably the strongest evidence we have of dark matter as something fundamentally different than protons, neutrons, and electrons. The next galaxy cluster I'm going to point out is this one, Max J0717.5 plus 3745. So names like this are rather common these days because, and I've heard them called telephone numbers by some of my colleagues. And the reason these names exist, why they're so long, is because modern astronomical surveys are just collecting so many objects. They're detecting so many objects. There are so many galaxy clusters, so many stars, so many galaxies that are being observed. And really the only way to sort of denote them, the only sensible way astronomers have found to denote them that's not completely, that has some information in it, is to use the coordinates. So for this cluster, Max J, basically, Max is the survey that found it. And then the J tells you, sort of the coordinate system, sort of the basics of the coordinate system. And then these are the coordinates themselves. So this is found at right ascension, 7 hours, 17.5 minutes, and declinations plus 37 degrees, 45 minutes. So that's what it means for this to have that name. And this is a merging system as well, where 4 smaller clusters are all merging into one larger cluster. What's really interesting about this cluster is this long pink filament right here with radio emission. And this long pink filament denotes basically the sonic boom of this collision. So because the ICM is a gas, it has a sound speed. Because it has a sound speed, you can actually travel faster than that sound speed. Sound speed's really fast. It's like 1,000 kilometers per second. So you have to be traveling even faster to create these shock waves. But this is a shock wave and a sonic boom arising from the fact that these two clusters, or two of these subclusters, collided at a speed faster than the sound speed of one cluster's gas. Finally, the most interesting cluster, probably the most interesting cluster of the bunch, is this one, Max J1149.5 plus 2223, which has had some really interesting transient events happen. And the transient occurred because this galaxy right here, the one right in the middle of this circle, is actually lensing this blue spiral galaxy right next to it 4 times in this image. So you can see one image of it here, another one here, a third one here, and there's a 4th one that's not as important right now. That's elsewhere. Now, what's really cool about this particular system is that this spiral galaxy, this one that I'm pointed to right now, this galaxy actually had a supernova go off in it. And those supernovae are short-lived events. And as I mentioned before, if you have multiple images, you may not see the same occurrence happen at the same time in each one when you're dealing with gravitational lensing. And in fact, based off of how this lensing configuration, and the mass, they were able to predict that when after the supernova went off in this galaxy, they would see it go off in this galaxy about a year later. There's actually also had a prediction for this this image of the galaxy, but that was 20. It was supposed to be observable 20 years before the original supernova was found. So there's no way to see that one. But they actually had a prediction for the supernova to be observed in this particular galaxy based off of what they observed in this one. And it turns out that it fell right within the prediction window. They kept observing it, and voila, that supernova arrived exactly when they expected it to, or exactly within the range they expected it to. What's even stranger is that there's an even stranger alignment that happened with these two galaxies, in that some very careful analysis, they saw a brightening of this galaxy in one of the images that they couldn't explain until they looked really carefully at the data, and they realized that probably what happened is that a single star within this galaxy actually was properly aligned, was aligned well enough that it actually enhanced the brightness to where it was observable with Hubble. So this is a purely Hubble image. And it's studies like this that actually allow us to observe the extremely distant universe, using these galaxy clusters actually as sort of a cosmic telescope to observe what's happening behind them, or further away from us, or further back in time than we could ever hope to find without the cluster there. So this is where I'm going to end my talk. I'm just going to put up the image, put up the pictures of these 3 Science Olympiad approved galaxy clusters for you to view. So hopefully everybody's learned a few things about galaxies, gas, and dark matter, and how they interact in these clusters, and what we can learn from these structures. So if there are any questions, feel free to ask me now.
Thank you so much, Dr. Ehlert. That was really amazing. And I think you did a really awesome job of tying in Science Olympiad to your research, which I thought was really cool. I was wondering, so what do you think are the next directions in the studies of galaxy clusters? Like, what future observatories are going to come online in the next decade that might revolutionize our understanding?
So I mentioned redshift, and how going to higher redshifts means you're looking further back in time. And I think that's where the most interesting questions are going to be moving forward. And it's going to be a mix of X-ray and optical. I think there's a lot of interest to seeing sort of the very earliest stages of these structures forming, sort of what turns into the really massive structures today, or the really massive structures later on. That's where I think it's going to be the most interesting, is sort of seeing, by looking way back, sort of how the physics changes, how the physical processes change, or sort of what contributions are bigger or smaller in those higher redshift clusters versus the ones we're able to observe more easily these days. But yeah, and that's the thing, is that you kind of just need bigger mirrors, you need bigger scopes, you need better detectors, because the further back in time you go, everything, or the further back in redshift you go, everything gets fainter, everything gets smaller. You have to, the reason we have things sort of nearby more frequently is because they're the easiest to find. And they're the easiest to get a lot of signal on. So to really push things back, you need bigger and better.
I just want to tell you that that was outstanding. The sequencing that you put together of content and topics and adding the deep sky objects in, the hardest thing we have with especially the young team members who are just learning the content for astronomy, they have a hard time understanding that the different topics that we have in the event description, they're sort of treated like different things. We need to know about this, we need to know about that, but they don't get an understanding of how it all so beautifully fits together. But for the big picture of what's going on. I mean, that was really, really well done. Thank you.
Well, I'm flattered. Thank you.
Well done.
Yeah, absolutely. I want to say thanks and echo both Donna and Dad. It's always really cool to get to see these objects that we work with in the event kind of explored even more in depth by experts in the field. And I think it's a really, really valuable resource, and it's awesome that you wanted to come on and talk to us about this. Thank you.
Well, thank you for having me.
Dr. Eller, thank you so much for your talk. I just had one, I guess, question, kind of a follow-up to Tad's question. So I know that the James Webb Space Telescope is, planning to come be launched in, I guess, the coming years. So is that one of the goals of the James Webb Space Telescope, to look back further in time so we can, I guess, get an idea of the earlier stages in galaxy cluster evolution?
Yes. Yes. So James Webb actually observed light that's sort of what's known as the near infrared, as opposed to the optical, like Hubble. Mm-hmm. And one of the reasons for that is because if you have a galaxy at a redshift that we typically, if you're looking at a galaxy cluster, not only actually the wavelengths change because of the redshift. So that's where the name comes from, redshift. It's because when things are moving away, they look redder. So actually, to observe a galaxy cluster at sort of the same intrinsic wavelengths that's further away, you actually need to go to longer wavelengths in your detector. So it's very much designed to look further back than Hubble. It's bigger, but it also has that wavelength tuning, and to really ensure that it can see galaxies way, way back, and that it's very efficient at detecting those galaxies way, way back.
All right. Thank you so much for your talk.
Well, you are welcome.
I'm curious, since you mentioned James Webb, what sort of stuff is happening at Marshall Space Flight specifically in support of James Webb, if there's anything going on down there for it?
So there's not much in terms of James Webb. There's lots and lots of work. So Marshall primarily does the rockets. They have astrophysics, obviously. Mm-hmm. They have some astrophysics programs. In particular, Marshall runs the Chandra program office. So it's a lot of the X-ray work there. The majority of the center is building the SLS rocket that's going to take astronauts to the moon. There's involvement in Gateway. There's involvement in the lunar lander. Those are kind of the really big things going on at Marshall. They're sort of taking the lead on a lot of that. I'm in no position to really say anything more than that, but about those things. But yeah, in terms of the astrophysics, I mean, there's a lot of X-ray and gamma ray projects that are ongoing, and some other optics work that would be useful sort of at optical wavelengths. James Webb is at a different center. I want to say Goddard, but I'm not 100% on that.
Mm-hmm. Cool. Thank you.